All right. So homotopy equivalence. Okay, so I'm going to define this in kind of a funny way. All right. So let's I'm going to define a category, right? And then I'm going to define a homotopy equivalence to be an isomorphism in that category. So definition. So the homotopy category H top, right, is specified by in the following way. So this is really the naive, maybe I should put this is the naive homotopy category. There's other homotopy categories that people talk about a lot, and this is not the kind of fancy version. This is kind of the most basic version of this stuff. So the objects are so this is kind of a very general theme in math, is that we often make categories where the objects are exactly the same. So there's another another good example of this is what are called derived categories. So in both these categories, you keep your objects the same, but then you change your morphisms. And I actually have a bunch of YouTube videos on that for those that are interested. Okay, so the morphisms are, so what is this thing if I have two topological spaces? Well, this will just be homotopy classes of maps. Okay, so that's the homotopy category. Okay, so let me give some kind of okay. So now I said I was going to define homotopy equivalence. So there's a theorem that we need to prove this is that this is actually a category, right? There's some stuff that we need to deal with, right? But let's give a definition, right? So, right, an isomorphism in H top is a homotopy equivalence. That's one way of saying it. Okay? Well, let's say, yeah, an isomorphism in this category, or let's say two isomorphic objects are homotopy equivalent. That's probably a better way of saying it, because I'm going to try to make some choices in a second. And then, an isomorphism is, okay, and you'll see. Okay, but yeah, I don't want to exactly think of it as the set of things, but I'll think of it as a particular one that such that there exists a homotopy inverse. And I'll say that again. An isomorphism in this category is a homotopy equivalence, and so I'm going to be a little bit abusive here, and we'll write this for homotopy equivalent spaces. Spaces. All right. So okay. So what's the identity? So an important point is that so what's the identity look like in what do identities look like in this category? So note. So identities are maps, or continuous maps. So identities in the homotopy category are continuous maps homotopic to the identity, right? So now you just don't need something to be the identity on the nose. You just need it to be the identity up to homotopy. So the concrete way that we work with this is that a homotopy equivalence is a map, right? Is a map x to y with a homotopy inverse. Y to x. Okay, and so maybe do it like this. Okay, and so what does this mean? So this means that two things, right? It means that F composed with G, right, is homotopic to the identity on Y, and G composed with F is homotopic to the identity on X. Okay, so we have these two descriptions. So that's what a homotopy equivalence is. If you think about this in terms of classes, in like this matching this, it gets a little bit confusing because we haven't shown that this is a category. Okay, so there's some issues here. Okay, let me kind of highlight these issues. Okay, so there's a theorem that we want to describe, or kind of indicate the proof here, is that H top is a category. And so this is really goes along with the homotopy being, if two things. Okay, so let me kind of just draw the two issues here. So there's two issues. Okay, so issue one is there's vertical composition issue, right? So here, so let me draw it. Well, okay, so I guess I'm going to draw the horizontal one first. Okay, so I can have a map like this, F0, and I can have a map. I could have two maps here, and they could be homotopic, right? And then I could have another map here, and these could be homotopic by some homotopy G, right? And so what we need to show is we need. So this is like the horizontal issue. So this horizontal composition issue, right? So so we need that G0 and F0, right? So we need some sort of operation between these two things. So we need some sort of like F, G, and then we need G1, F1. Okay, so this is issue one. Issue two is the same thing, but vertical composition, right? So I could have X going to Y, and then I could have three things. Okay, so I could have F, G, and H, and then if this one's homotopic, right, by some F, and this one's homotopic by some G, right? We need to show, what we want is do we get this one? Right? Is this the one we get? So is there some way to get this? So so this is I guess the transitive issue in the equivalence argument. So we're not going to do, I guess maybe the reflexive and symmetric properties are the easiest ones, but this is like transitivity, and so really so this is the vertical composition of homotopies. Right. Okay, so those are the two issues that we need to deal with in order to make the composition of morphisms well defined. All right. Okay, and so to deal with so how do we compose homotopies? So there's the solution of the vertical issue is the easier one to resolve. So okay, so composing. Okay, so let's do the vertical one first. Okay, so this one's not so bad. So this is just like the way that we compose paths. Okay, so this is just like the composition of paths here. So here, right, so this is the concatenation of two things, right? And so what we'll do is, okay, so we need to figure out how we want to compose two homotopies. Right, so maybe I'll draw the picture over here, and then I'll fill that in a second. Right, so what we have is okay. So what we have is we have two homotopies, right? Right. So we have the homotopy here and the homotopy here, right? And so what we want to do is we want to just kind of like take this one to this and this one to this in like double speed, right? So, so here you'll see a lot of diagrams like this, and I guess I want to show you them. So here's and this is the speed up function. So we're kind of going to play it in fast forward, right? So here's a half, and so we need to run through the first homotopy f at twice the speed. So here's 1, and here's 1 over here, okay? And so we need to go twice the speed, and so this slope here, this is just going to be 2t, right? Okay, and then this one also needs to start down from 0 and go back up. So this is for g, and then this one's for h, okay? But, we're going to have this thing, you have to do the whole y-intercept thing, and this thing's 2t minus 1. Okay, so what we've done is we're just going to like do the first homotopy. Then once we get here and here, the functions are going to agree. So this is like where h is, right? This is where f starts, or sorry, this is where g is. So this is where f is. F is at this line, g is at this line, and then h is at this line. So we kind of do the homotopy here to get to g, and then we do the homotopy here to get to h. And so, so this is f of, so now we can write this. So this is f of 2t x for t in 0 to 1/2, right? And then this one is g of 2t minus 1 x. And now this goes for t in 1/2 to 1. All right, so that's the way of composing the vertical issues. So this takes care of the vertical. So the concatenation takes care of the vertical composition. So yeah, okay. So all right. Okay. So there's finally, let me just say about the vertical. Just one last bit about the vertical thing. Is that there's this let's just keep thinking about the adjoint perspective. Okay, and so it's the same thing as this concatenation. So we have f, right? This is from I cross x. So we have two of these. We have f and g, I cross x to y here. And so this is the same thing as, via adjunction, a map from I into the space of maps. Right? And this is a map from the space here. Okay? So really, what you can think of is that if this is the space of maps, so this is the space of maps, right? The first thing is we have this f thing, and so f, so we have our first map here, and then we have g is a point. So now, so these maps are points now, okay? Because so the maps from x to y, using the compact open topology, they're points, and then f is really a path in here. Okay, so we have two paths like that. Right? And so really what we just did is we actually did this composition of homotopies is really just concatenation of paths like in the first video. So because we put in the compact open topology work, it's what we did was just as hard as concatenation of paths. Okay? So now let's deal with the horizontal composition. Okay, so we're given. So what we can do is we can just kind of like take two things, and for each, so we have two things. So we have for each t and s, we get a map from here x to z. So again, what we're looking at. So I guess I can just draw it again here. So we have x, y, z, right? We have two maps here, and two maps here, right? And then we want to know that composition of morphisms is well defined in the homotopy category. So G0, G1, right? So that it doesn't depend on the choice of representative. Okay, so here we can take the pieces of the maps and we get these two things here. Okay, so all right, so let's look at what we have. So in this situation here, so this, so we have really, G S f of T S Tx, right? And this is a map from I cross X into Z. All right, so let's draw what happens at each of these points. So here is, we'll draw the ST plane, TS, right? And then here's one, right? And then we have this box here, okay? And then we can kind of describe what happens at each of these things. So here's G0. So when they're both 0, 0, it's the composition of G and F. And I'm going to just omit the composition symbol here. So this is G0 at F0. And then here, this boundary line here, right? So this is G0, and then I'm going to move this homotopy here, right? And then eventually at this point, we get to G0, F1. So I'm looking at what this function looks like at the various parts here, okay? So the other thing that happens is that here we get to G1, F1, right? And we go along by this G changing, right? So as we change S, right, the G part is changing. So this is G composed with, okay, so we're not writing the composition map because it'll get too cluttery. Okay, and then here we have G1 F like this, and then and that goes from here, G1 F0, and then we have this G's changing here. So the F0s are fixed because this is where T is equal to 0, this is where T is equal to 1, this is where, this line is where S is equal to 0. So, we have these different homotopies, and so any path here, right? Right. So any path from here to here that has the appropriate speed. So path with from 0, 0 to 1, 1 with appropriate speed, so that the path is covered in so that it only goes in time 1, right? Gives the homotopy. Okay, and look about this interesting part here, right? Is that so this thing here, we've kind of defined some composition, right? Okay, so we need to start here and we need to start here. And what I want to say is that this composition here, we could have taken some other path like this, right? Or some other path like this, right? But the composition, so let's call this thing here. So this is the composition of up to homotopy. Okay, so it is well defined, but we don't just get the simple like one then the other. But here you have to, this thing's well defined. You have to do some sort of choice, but it's not canonically defined. You have a whole homotopy class of them. But this homotopy is a little bit different, right? So this homotopy is, so you're always going to have this part fixed and this part fixed. So the endpoints are fixed, right? So this thing is called a fixed endpoint homotopy here. Okay. Okay, so let me just say that we're done with the discussion on the homotopy category, right? So the composition of morphisms is well defined, so we've kind of dealt with these issues. One thing that I just want to kind of go into this discussion because these other types of homotopies are going to always appear. They're going to keep reappearing like they did now. And I said I wasn't going to introduce them until, I told myself I wasn't going to introduce these variants of homotopies until they came. And this is the first time we saw one, right? And so they're just going to like crop up, okay? Let's talk about the variants of homotopies. let's see. Yeah, I'm going to keep it as part of this video. It's probably going to be around 30-minute video, I guess. So of homotopy. Okay, so this is just so other things. So there's the first thing I want to talk about is the relative homotopy, which is going to be okay. So the primary example is this thing where you have you have two paths here, and then these are homotopic. So here you have A. Okay, you'll see what this is going to go. So this is just going to X is I, and Y is a space. So this is a fixed point. This is going to be like some fixed endpoint homotopy. Okay, and now I'm going to fill in what A, X, and Y are in this definition. So the ingredients for a relative homotopy, right? So we're going to need X as a topological space. We're going to need a subspace. And then we're going to need two maps, right? So we're going to need two maps from X to, so we have F and G, like this. So they're going to be equalized by A. Okay, so what does that mean, right? So this means that F restricted to A is equal to G restricted to A. Okay, so yeah, so you could actually write an equalizer diagram where you have like A in here, and then the composition of this map and this map are the same. Okay, so this is what the relative homotopy is. And so I've kind of given you the setup, and then on the next slide I will give you the definition. Okay, so so definition under that setup. So homotopy like this, relative to A. Okay, so this is relative to A. So this capital A here has nothing to do with that set. Okay, is a homotopy. Oh, I guess I should say do it like this. Like a homotopy blah is relative to A if and only if the following things holds, right? So for all t in the interval, f of t is the same thing as the previous two things, right? So we had these two things that were equalizing A, but we also need this thing to equalize A. Okay, so let's look at what happens here. So when A is these two endpoints, right? So we have like two paths here, gamma 1 and gamma 2. And so what we need is we have this paths so we have a sequence of paths. But not only do these 2 points agree on A, right? But all the things that interpolate these two things also agree on A, right? That's what this thing is. Okay, so it's a generalization of this, and yeah. Okay, so that's a relative homotopy, and then there's another thing called a based homotopy that we'll need. Okay, so what's a based homotopy? So the setup is the same as before. So we get a pair of maps. Well, not the same. Sorry, it's not the same as before. This is different. Okay, so we can have F0 and F1, right? So this is in the category of topological pairs, right? So this is so this thing here is so this is a map of pairs. These are maps of pairs. Okay, so this means that this thing had to be in a subset of that. So these are two maps, right? So this thing here, F0 F1. So this thing is called a based homotopy. Right? If and only if. Right? So this thing here. So you can consider this as a map of, say, on x's and y's first. But this is a map of topological. So for each t, right, this is a map of pairs. Right? And such that that f at 0 is f0 and f at 1 is f1. Okay, so it's just a map of pairs. It says it's you know, I mean, you could have guessed what the definition was. Okay, so the most important subexample of the based homotopy is the important subexample is the pointed important subexample, right? Is homotopies in of pointed topological spaces. And so I think, you know, if we wanted to be, if we were smarter, we could have set up the theory of doing everything based first, I guess. I haven't thought about what this is nice. But maybe we should have defined, like if we were trying to be, maybe it's not so clear that it's not really a good exposition because it's, you know, you don't really know what's going on. But I guess we could have set up the entire theory just to be in terms of these pairs, right? And then specialize them to the cases of topological spaces and pointed topological spaces. But yeah, but maybe that's not the best approach. I'm not sure. Okay, so I'm going to just end with two examples. Okay, so two examples. Right. So okay. We're not done. We're not done. We talked about all these homotopies. And now I need to say something about. So we had all those examples of homotopies. So where are the examples? Yeah. So we had these examples where we like had R3 and we removed a circle, et cetera, like this. Okay. And we ended up getting here. So all of these examples that I've been doing are just kind of like continuously deforming stuff, right? So so there's kind of a, okay, so now I'm back on this homotopy equivalence thing. I've kind of talked about all these homotopies. I've gotten that out of the way. Now I'm going to use it freely. Okay. Actually, I'm going to stop here and then start the video, a new video now.